Hi, this is Miss Logan. This is a flipped lesson on the inclined plane. What is an inclined plane? An inclined plane is a simple machine. There are 6 different simple machines that scientists have identified. You may have worked with these in middle school or maybe even elementary school. The inclined plane is one of them. This is when a large flat object is tilted slightly higher on one end or another. What's going on in an inclined plane? The 2 forces that are always acting upon an object is first the force of gravity. This is always in the downward direction. Force normal is always perpendicular to the inclined surface. So if it's on an angle, our normal force is also on an angle. Normal force, as I said, are always directed perpendicular to the surface. This is the situation we've seen so far. Something sitting flat, gravity is down, and then force normal is opposite. However, it's a little bit different when we're on an inclined plane. Gravity is still going straight down, but our force normal is going at an angle. Let's go through the steps when we set up an inclined plane problem. The first step is to label the direction of force normal and our force of gravity. So remember, our force of gravity is also equal to the weight, which is mass times gravity. Then we have force normal, which is going perpendicular to the inclined plane. Our second step is to mark the direction of acceleration. If we look at this, we can tell that this object would be sliding downwards, so our acceleration would also be going downwards. This is the most important part and what I think is often the most challenging. What we need to do is actually change our coordinate plane. Here's what we're used to. But we're not going to use this in this situation. We're going to actually tilt it on its slide. So my x direction is going at an angle, and my y direction is also going at an angle. However, it still looks like x is close to horizontal and y is at an angle. This will help us, and you'll see that in our next step. Now that we've set up our coordinate plane, we can do some trigonometry and actually start solving for these different parts. So that we know that force gravity is going downwards. However, we need to break it up in our y direction and our x direction. Let's use trigonometry to figure out both of these sides. Okay, so now we can break it up in our x and y direction. So we would know that this side here is mg cosine theta, and this side here is mg sine theta. So I actually moved this part of gravity up here. This is going opposite in our x direction. Then I have mg cosine theta, which is opposite our force normal. Let's see how we'll actually use that in a problem. Now we can use Newton's second law for both the x and the y directions. So in our x direction, we know the force equals mass times acceleration. We also know that that's equal to mg sine theta. So we can use this to figure out our acceleration. In the y direction though, we know this thing is at rest. This is how we're figuring out what our force normal is. Remember, it's opposite of my y portion of gravity, which is mg cosine theta. So that is what is equal to our force normal. All right, let's do a sample problem together. So the first step is to always label all the forces. The only one that I would like to add here is our acceleration, just so we can visualize where it's going. Okay, so first ask, what are the components of gravity? This is always our first step, breaking down our components of gravity. we have our y here and our x here. So we know that our x component of gravity is equal to mg sine theta. Let's assume that this box is equal to 100 kilograms as well. So right now, remember, we're solving for force of gravity in the x direction. Let's plug in my numbers. 100, 9.8, and sine of 30 degrees, which I got from right here. I'm going to get for my answer 490 newtons. That's my force of gravity in the x direction. Now for my force of gravity in my y direction. We have mg cosine theta. Let's plug in our numbers. 100 times 9.8 times cosine 30 degrees. I'm going to get 849 newtons. So sometimes I may also be asked to solve for this regular force gravity. I'm really not going to worry about that because we care about the x and the y components. Okay, our next part, what is the force normal? So let's remind ourselves that right here we had 849 newtons, and then in this direction we had 490 newtons. I got that from my cosine down here and my sine on this side. So let's talk about the force normal. We can see that my force normal is equal to the opposite side. So my force normal would be equal to 849 newtons. It's opposite of my y component of gravity. Okay, from our last slide, we know that my force normal is 849. That is really going to help us. My equation for friction, force of friction, equals mu times force normal. Let's assume my mu is equal to 0.3. Now I just need to plug in. My mu is 0.3. My force normal is 849. So my answer is going to be 255 newtons. Next, what is the net force on this object? Okay, so we know that my force of friction is 255, and over here we know that I have 490 newtons. Remember, I got this from my x component of gravity. So my force net, I can just subtract these two. So 490 minus 225 is going to equal 235 newtons. Now if I don't have friction, I don't have to worry about this. It would just be 490 newtons. And the last part, what is my acceleration? So remember, I would use Newton's second law, F equals ma. So what should I use for this force here? We should be using the net force, which we figured out from the previous slide. So let's plug in our numbers. I have 235 equals my mass times acceleration. So for my answer, I'm going to get 2.35 meters per second squared. So through these slides, I solved for almost all of the variables that we would solve for in different problems. However, as you can tell, this initial setup and figuring out my x and y components are the most important part. Alright, so please work on these follow-up questions. During class over the next few days, we will work on the setup for these problems and solving for different variables.